the Institute of Mathematics, Statistics, and Scientific Computing. It is a great pleasure to introduce you guys to Dr. Paolo Piccione. He is actually, his undergrad was in mathematics by the Universidade de Studi de Roma e La Sapienza. And he got his PhD at Pennsylvania State. I think this was Penn State State College. And he got his livre docência, his associate professor by University of São Paulo. At University of São Paulo, he is now a full professor, and he has contributed quite a lot to our science. As you guys can see, I have like a short list here, because it's not something I can get from top of my head, but he is a full member at the Brazilian Science Academy since 2012. He's also part of the Scientific and Technical Council of the Institute of Mathematics, Pure Mathematics and Applied Mathematics, and also member of the International Mathematical Union. He is one of the coordinators of the area of mathematics and statistics at FAPESP, and he is, by the way, look at this, comendador, I do not know how to translate that to English, on the National Order of Scientific Merit in Brazil. And he's also got the title of Cavaliere dell'Ordine della Stella d'Italia, which was given by the Italian president, granted by the Italian president. Throughout his career, Professor Paolo has done quite a lot in terms of science. He was the president of the Brazilian Society of Mathematics, and he was also in different committees and in addition to councils. I will give a little bit of highlight to the National Council of Scientific Development and also Technological Development, and also at the University of São Paulo. He's a specialist in differential geometry. His research includes themes like variational calculus, and this is a bunch of subjects that I actually do not know how to say in proper English in mathematics, but in Português it would be problemas variacionais geométricos, teoria da bifurcação, geometria riemanniana e teoria de Morse, geometria simplética e sistemas Hamiltonianos. Obrigado. He is the coordinator of a thematic project at FAPESP, where he's looking at the development of algebraic techniques, topological and analytical, in terms of differential geometry and geometry. Oh, that's it. He is also a research fellow at CNPq at level 1A and associate editor of the journal Matemática contemporânea. He is the scientific director of the Brazilian Center of Geometry, and we welcome Dr. Paolo to this talk, which is titled Conformal Curvatures. Professor Paolo, thank you so much, and I pass it on to you.
Okay, thank you very much for this nice introduction. I feel a little embarrassed actually, but and I want to apologize for the delay. I'm in a kind of remote place in China, and it's internet connection is somewhat tricky. And I was very pleased when I was invited to give this talk. And I decided to talk a little bit about, since this is a workshop related to the Center for Brazilian Center for Geometry, I thought I should speak about something very geometrical, and that's why I decided to talk about curvature, and in particular curvature in conformal geometry. and which is a conformal geometry is an ambient where analysis meets geometry. The theory of PDEs enters with all its strength inside differential geometry, and this is the area that I've been working in the last few years. So let me tell you a little bit what is geometry, what is curvature in general, what I think about, how I think about curvature, and before we get into the conformal topic. So let's see, maybe we can agree with this definition of curvature. Any geometric theory more or less has a linear model, and the curvature in a geometric theory is a quantity that measures locally how much a given structure deviates from the linear model. For instance, if you think about planar curves, the curvature is a quantity that tells you how much the curve bends away from a straight line. The straight line would be the linear model for the geometry of curves, right? So the curvature of a curve is a measure of how much the curve is not a line. If you go up one dimension, then we have surfaces. The linear model for surfaces are planes, and so the curvature of a surface should tell you how much the surface is non-flat, is not a plane. In Riemannian geometry, the linear model are Euclidean spaces. And so the curvature should be a measure of how much a Riemannian manifold deviates from a Euclidean space. Okay? In conformal geometry, that's what we will discuss in this talk. And I have to warn you that according to the definition above, there are some geometries that do not have curvature. And the most famous example is symplectic geometry, where the Darboux theorem says that you cannot distinguish locally any symplectic manifold from the linear model. The linear models for symplectic geometry are spaces R2n, even dimensional spaces R2n with the canonical symplectic form. And every symplectic manifold locally looks like the linear model. So, in other words, there is no curvature in symplectic geometry, according to this definition. So, I want to address two basic questions related to curvature. The first question is rigidity. Suppose that you're studying some geometric model and you know its curvature, and you want to know whether you can then reconstruct the space just from the curvature. Okay, so how does curvature characterize a space? Usually this problem is related to some structural equations that should tell you how the model is described just using curvature, okay? So in particular, the answer to this question, like you can characterize a space with curvature if all local invariants of this space are somewhat related to curvature, right? The second question is a question of deformation. Suppose that you're studying a class of models in some geometry and you want to know whether you can perturb a metric in this class in such a way that the curvature becomes as easy as possible. For instance, 0 or constant, okay? And in this case, how many different deformations exist to make the curvature 0 or constant? Is there a unique way or maybe more than one way? So this is the type of problems that I will discuss in this talk. I do not see you, and in case you would like to stop me at any time, you should really speak loud, because I do not see you, in case you raise your hands. So let's start with this easy example, planar curves. So a planar curve is just a smooth map from an interval to Rn, and the only invariant for a curve is its arc length. There are no other intrinsic invariants, okay? So there is no intrinsic notion of curvature. Any two curves that have the same length are isometric intrinsically. Okay. Now, if you want to study extrinsic curvature, that is, if you want to study how this curve sits inside the ambient space, then there is a curvature. And the curvature is given exactly by the absolute value of the second derivative of the curve, and we're thinking of parameterization by arc length, of course. So gamma prime is the unit tangent vector. The curve is a straight line if the unit tangent vector is constant, and so a correct measure for the curvature would be the derivative of the unit tangent vector. So it's the second derivative of this function gamma, okay? And there is a classical theorem that says that, in fact, if you know the curvature, if you know this curvature function, basically it's just an integration problem, okay? So for planar curves, the curvature is a complete invariant. If you consider curves in space, then there are other notions of curvature. For instance, in 3 space, there is a quantity called the torsion, which is defined with these formulas. So you take the frame, so it's given by the tangent, the normal, and the binormal. And the curve is planar when this binormal is constant. So basically, a measure of non-planarity for a curve would be the derivative of this binormal. And then you realize immediately that the component of the derivative of the binormal with respect to the tangent direction or the binormal direction, this is 0. So really the only quantity that counts is the component of b prime in the normal direction. And so the torsion is defined to be the derivative of b, inner product with the normal vector, okay? And the fundamental theory, so we have 2 notions of curvature for curves in space, curvature and torsion. And the fundamental theorem of curves says that, in fact, once you know these 2 functions, then you can recover up to rigid motion the curve itself. And the proof of this uses, of course, the formulas, the Frenet-Serre formulas given by this thing here. And so integrating these equations would give you the function gamma itself. Okay, so these are the structural equations that I was mentioning at the beginning of my talk. There are some higher dimensional extension of these notions for curves in n-dimensional spaces. Okay. Let's go to the case of surfaces in space. So let's consider a surface in R3. Let's take a point of the surface, and we define the curvature of the surface at this point to be the average of all possible curvature of curves on the surface that pass through P. Okay. So you take all possible curves on the surface that pass through P, you take their curvature at P, and you take an average. Okay. And then if you're smart enough, you see that in fact it's enough to consider only curves that are obtained as planar sections. And in fact, it is enough to consider only curves that correspond to normal planar sections. So given a point, you consider the bundle of normal planes passing through this point and the corresponding surfaces, the corresponding intersections with the surface. You have a one parameter family of curves here, parameterized by this projective line. And among all these curves, there are two special curves that possess the minimal and the maximal curvature possible. These are denoted by K1 and K2. And so there are two possible means that you can do with these two numbers. You can either take the arithmetic mean, and you call it mean curvature, or you take like up to a square root the geometric mean of these two numbers, and you call these the Gaussian curvature. So two notions of curvature for surfaces, okay? Now we know that the study of surfaces was basically initiated by Gauss, who made a very important discovery, which he called in fact the Theorema Egregium in 1828. And this theorem says that in fact this quantity here, the Gaussian curvature, is intrinsic. It does not depend on how the surface sits in R3. It can be computed only from the metric of the surface, okay? He proved this by showing that in fact this number can be characterized as the ratio of areas. Like you take a small portion of a surface and you take a tangent, you take the projection of this small portion on the tangent plane, compare the areas, and this number is the Gaussian curvature. When you know the Gaussian curvature, you can then know the topology of your surface, thanks to this important theorem called the Gauss-Bonnet theorem, that tells you that if you integrate on the surface the curvature, you get the most important topological invariant of a surface, which is called the Euler characteristic. So this tells you everything about the shape of the topology of your surface. Okay, so you have rigidity. You give me the curvature, the Gaussian curvature function, and I'll tell you what surface this is, just by integrating. Okay, let's see the question of deforming Gaussian curvature. Can in the world of closed surfaces, can I perturb a surface so that its curvature becomes constant? The answer is yes, and this is precisely what the uniformization theorem says. This is a very important theorem that was proven at the end of the 19th century by basically Poincaré, Klein, and Koeppe. And this theorem says that if you have a simply connected complete surface, then you can change the metric conformally, and so that the space becomes either a round sphere, or a Euclidean flat space, or a plane with constant negative curvature, okay? A conformal metric is a metric which is obtained by multiplying the scalar product at each tangent space by a factor, by a positive factor, okay? So at each point of the surface we have a different factor, and so conformal metric is basically on a surface is basically given by a smooth positive map on the surface. Okay. This is an extremely important theorem because it opens many areas of research. For instance, in complex analysis, we have canonical models for Riemannian surfaces using spheres, quotients of spheres, Euclidean planes, and the hyperbolic plane. And also, this theorem lays the foundation for the theory of geometric PDEs, because in fact, this can be thought also as a theorem for PDEs. So if you make a conformal change and you consider the conformal factor, then conditions on the Gaussian curvature become conditional the partial derivatives of this conformal factor. So from equating the Gaussian curvature to a constant, you get a certain PDE, which is usually an elliptic nonlinear PDE that I will describe in a moment. So let me tell you how the curvature is related now to differential operators. Okay. Surfaces possess a very important differential operator, which is called the Laplace-Beltrami operator, which is defined with this formula here, where G is the metric, the Gij with these high indexes are the coefficients of the inverse of the metric G, and this absolute value of G means the determinant of the G. So this is a formula given in coordinates. You see, you take function u, you differentiate with respect to the jth variable, you multiply by this positive definite matrix, and you differentiate once more. So this is a strongly elliptic operator due to the fact that this matrix here is positive definite. For instance, when the matrix is flat, this is just the usual Laplacian. And when the metric is conformally flat like this, so you have flat metric times this factor, this exponential factor, the Laplacian is just the inverse of the exponential factor times the usual Laplacian here, okay? Now, the reason why this operator is related to curvature is that if you make a conformal change of the metric, the Laplacian is transformed in this way. So it's a very easy transformation rule. Basically, the Laplacian is multiplied by the inverse of the same factor, and the curvature of the new metric is satisfies this equation here, which you see it's an elliptic equation. The highest order term is the Laplacian, and here you have this is the linear term in the conformal factor. So this is a linear elliptic equation, which is, you can, for instance, which is equal to a constant or zero, for instance. So conformal changes of the Gaussian curvature are studied using a linear elliptic equation on a surface. Okay? By the way, this is called Liouville's equation. Let's go to now Riemannian manifolds. Let's see what time you're doing with the time. So a Riemannian manifold is a space where you can do geometry and analysis. You can compute angles between vectors. You can compute length of curves. You can compute distances, geodesics. You can compute volumes. You can compute areas of any submanifold. And you can define these differential operators like the Levi-Civita connection. You can do parallel transport. You have gradient and divergence, so you have Laplacian in particular if you mix these two. And the curvature here is defined as an invariant, of course, of order 2. We have seen so far that all the curvatures we have met so far are defined by second derivatives, okay? For a Riemannian manifold, the definition of curvature is not so, how do you say, clear as it is for Persa surfaces. It uses this strange formula here. So basically, the curvature is now a 1-3 tensor. Means that it's a function that takes 3 tangent vectors and produces 1 tangent vector as a result. And basically, it tells you how much taking covariant derivatives is non-commutative in a sense. Well, kind of. So when you apply this is usually the way you apply the curvature tensor. There's 2 arguments inside parentheses and 1 argument outside, which is where you apply this operator on the left. This is the invariant definition of the curvature tensor. Okay. So how does the curvature tensor define a Riemannian manifold? What are the local Riemannian invariants? There is a beautiful series which was developed by Biles in the 20s that gives you a way of classifying all local geometric invariants of a Riemannian manifold. So the theorem proven in 1921 states basically the same. If you have a scalar invariant of a Riemannian metric, this is necessarily a polynomial in the components of the Riemann curvature tensor, its covariant derivatives, and possibly the coefficients of the metric and its inverse. That's all you have. So basically, all the local invariants are related to curvature. Okay? These are scalar invariants. Also, tensorial invariants can be classified using curvature tensors. Okay? This is a very important theorem that we will use sometimes later when we study conformal manifolds. Also, another way of describing locally a manifold, a Riemannian manifold using curvature is given by this theorem proved by Cartan initially and then extended to all dimensions by Ambrose and Higgs. That basically tells you this. Suppose that you have 2 Riemannian manifolds and you take a point in the first Riemannian manifold and a point in the second, and you choose an isometry between the corresponding tangent spaces. And you ask yourself, when there exists a local isometry now, this is like an infinitesimal isometry of the manifolds, and you want to know when this infinitesimal isometry is the derivative of a local isometry. So when there is a local isometry that extends this. And the answer is easy. When this linear map intertwines the curvature tensors and all its covariant derivatives at these points, then this is the necessary and sufficient condition to integrate this infinitesimal isometry to a local isometry. Okay, so once again, curvature and its covariant derivative at one point give you the manifold around that point. This is the analytic version of the theorem. Okay. Okay. Let me discuss now a little bit about deformation of metrics in Riemannian manifolds. So a generalization of the uniformization theorem for surfaces. The Yamabe problem has the following statement. Suppose you take a manifold, Riemann manifold, a compact, with dimension is greater than or equal to 3, and you ask yourself whether you can perturb your metric G to a conformal metric G hat in such a way that this special curvature here is called a scalar curvature become constant. Okay, this is a problem that was formulated in the late 50s, but it was only solved completely, basically, at the end of the 80s, due to a very interesting situation. Okay, so the way you study this problem is introducing a certain PDE. I'm sorry, this is a PDE. Which looks like this. Well, first of all, you have to be smart and you have to write the conformal factor using this weird power 4 over n minus 2. Notice that n is greater than or equal to 3. And if you do this, then the Yamabe equation, which is what describes the solution for this problem, can be written in this way here. So we have a dimensional constant here, Laplacian, function times u, so this is the linear part. But now in dimension greater than 2, we have a term here which is no longer linear, you see? So if you want to have constant curvature in the is negative, there's basically a unique solution of the Yamabe problem by a principle which is called the maximum principle in analysis. Okay? Okay, so let us remember this for later. Let's go to the conformal world now. Now the differential operator that seems to be relevant for conformal changes, maybe you can see it here, is the operator that appears on this side. It is a Laplacian plus this term of curvature here, and this is precisely the definition of the conformal Laplacian. Okay. Notice that this concept only depends on the dimension. Okay. This conformal Laplacian satisfies a nice formula when the metric is changed conformally. Basically, when the metric changes conformally, also this operator changes conformally with the similar factor to this, only changes with this dimension here, okay? So we take this equation to be the model for what we define to be a conformally covariant differential operator. This is the definition of a conformally covariant differential operator. A differential operator on a Riemannian manifold, depending on the metric, related to the metric. This means that the differential operator has coefficients which are obtained using metric invariance. So this is conformally covariant if it satisfies a formula similar to this one here. That is, the operator associated to a conformal metric is basically the same conformal factor times the differential operator. Okay? Do we know conformally covariant differential operators? Yes, we have met one here. This is the conformal Laplacian here. And then it was found another operator called the Panitz operator, whose definition is hell. It involves lots of geometric terms, scalar curvature here, Ricci curvature here, Laplacian here. But what we need to observe is that the highest order term is just the power of the Laplacian. This is the square of the Laplacian, so this is a fourth order term. Okay? And all these other terms are curvatures, okay? And there is a new term here. The zero order term is this QG, is a function that now satisfies some nice covariance properties by conformal changes. So people call this the Q curvature, okay? So this is the fourth dimensional analog for the scalar curvature. This is the zero order term of a conformally covariant differential operator, okay? So this has to be the proposal for conformal curvature. What is a conformal curvature? A conformal curvature for a metric would be a scalar quantity which is the coefficient of a conformally covariant differential operator. Okay? Typically the term of order is zero, like this Q curvature here, or the scalar curvature here, okay? This is a rather involved definition, of course, On the other hand, you see that as the geometry becomes more complicated, also the corresponding notion of curvature becomes more complicated, okay? Here we observe that for the definition of conformally covariant differential operators, sometimes you need higher order differential operators. For instance, the Q curvature is really defined better than for manifolds of dimension at least 4, okay? So higher order conformally covariant differential operators may require higher dimension. Now the thing is that, but how do we determine conformally covariant differential operators, or in general, conformal invariants? Is there a variance theory also for conformal manifolds? And this is where the school of Pfefferman comes in. So there are two constructions which were developed by Pfefferman and his collaborators. One of them is called the ambient metric construction. And so the idea is we want to find all conformal invariants using some metric invariants, okay? Usually this is done by considering a conformal manifold and embedding this conformal manifold into a higher dimensional Riemannian or pseudo-Riemannian manifold in a special way, so that the Riemannian invariants of the ambient give rise to conformal invariance of the initial manifold, okay? The ambient metric construction has as a model the embedding of the sphere in the light cone of a n+2, so you embed the n-dimensional sphere as a hypersurface of the light cone in an n+2 Minkowski space. So you take Rn+2 with a Minkowski norm, you take the light cone, you take a section with a plane, with a hyperplane, and you get a sphere. And the theorem is that the metric invariants for the Minkowski space become conformal invariants for the sphere. Okay? This is one known for the sphere, and what Pfefferman did was extend this to any compact manifold. So the idea is that you embed M as a hypersurface in an n+2 dimensional space. This n+2 dimensional space is endowed with a pseudo-Riemannian metric. And this pseudo-Riemannian metric, in fact, is Ricci flat. Okay? So it can be, the metric can be constructed locally using the Einstein equation. This is the Einstein equation with initial value given by the metric on M. Okay? So this is only a local construction. Basically, you obtain the Taylor's expansion for this Ricci flat metric in this n+2 dimensional space. But then the theorem is that the metric invariants of this pseudo-Riemannian metric become conformal invariants of the metric G. Okay? This is the ambient metric construction. There is another one also, very well known, also due to Pfefferman and his collaborators, which is called the Poincare metric construction. And here the model is again given by the sphere. You probably understood that the sphere has a very special role in conformal geometry. Now you look at the sphere as a conformal infinity of of a disk. The disk endowed with the hyperbolic metric, okay? Riemannian invariants of the disk become conformal invariants of the boundary at infinity, okay? So this is the model for the Poincare metric construction. In this case, you describe your conformal manifold M as the boundary of some manifold of dimension just n plus 1, not n plus 2, in such a way that the closure of this manifold admits a complete metric, like the Euclidean metric of the disk. But if you divide this metric by the square distance from the boundary, you get a complete metric on the interior of the space, which is also asymptotically hyperbolic. And in fact, it satisfies also now this Einstein equation. Now the Ricci is no longer 0, but it's the negative multiple of the metric itself, okay? So again, you obtain a local construction around this infinity of this asymptotically hyperbolic metric by looking at the equation. And the theorem is that metric invariants for the hyperbolic manifold correspond to conformal invariants of its boundary at infinity. Okay. So we have again a classification of all possible conformal invariants. Let me just say that using this construction, you get a lot of conformal invariants for manifolds. One of them is this Q curvature, and there are many more. There are these renormalized volume coefficients. There are the sigma k curvatures, and also this a family of operators, of conformally covariant operators, very important, called GJMS operators. Since my time is almost over, I want to use my last maybe couple of minutes to show you now a deformation result for one of these conformal problems. So just to mention one of my contributions to this theory about existence of conformal deformations with constant, say, scalar curvature. So the problem is now a problem on a non-compact manifold. I want to consider the round sphere of dimension m, but I want to remove from it a k-dimensional sphere in the equator, like an equator of dimension k, okay? So this becomes now a non-compact manifold, which has a nice metric, which is the round metric, which of course has constant curvature, but I want to find another metric in this conformal class, which has constant scalar curvature, but which is also complete, okay? So the Yamabe problem for non-compact manifolds now adds one condition, which is a condition at infinity. You want the metric to be complete. So I want a complete metric on a sphere of dimension m when I remove a k-dimensional equator with constant scalar curvature and which is conformal to the round metric, okay? So the theorem that can be proven is that if the dimension of this equator is not too big, does not exceed half of the dimension of the space, in fact this problem has infinitely many solutions, okay? And I think I'm capable to show you a proof of this fact, which uses some of the things that I mentioned so far. Just to show you what kind of technology enters in this kind of result. So let me try and give you the proof of the existence of infinitely many solutions. Okay, this is some graph, but maybe I can guide you through this. So you first observe that Sn minus Sk is the same as Rn minus Rk, just using stereographic projection, okay? Now, if you're smart enough to write the Euclidean with the flat metric here, flat metric. So you write the flat metric in this way. You write polar coordinates in dimension n minus k, and Euclidean coordinates in the other k dimensions, like this. And then you're free to divide by r squared. And so you get this metric here. And this metric is very famous because this is the metric of a sphere, and this is the metric of a hyperbolic space. So what I'm saying is that Sn minus Sk is conformally equivalent to this nice space here. Hyperbolic space times a sphere, okay? And so we have one solution for the Yamabe problem, for the singular Yamabe problem, because this metric here, the product metric, hyperbolic times round, is complete, of course, and it has constant scalar curvature, okay? Notice that this is positive exactly when k is not too big. You see, you have a negative factor here, you have a positive factor here, and so the sign of the curvature depends on k. If k is big, is negative. If n is big with respect to k, this is positive, okay? So here we have one solution for the Yamabe problem. Now let's find the other infinitely many. We observe that the hyperbolic space is non-compact, but it has lots of compact quotients. These are called compact hyperbolic manifolds, okay? They more or less look like this. Now, a compact hyperbolic surface has its fundamental group, which is, of course, finally generated, because every compact manifold has fundamental group which is finally generated, and it's also an algebraic group. It's a subgroup of SOK plus 1, 1. And in this situation, there's a famous theorem in group theory that tells you that this group is residually finite. This means that it has an infinite tunnel of finite index normal subgroups, okay? And finite index normal subgroup in topology becomes compact coverings. So from this infinite tunnel of finite index subgroups, we build an infinite tower of compact coverings, okay? So we have infinite tower of compact coverings. So we have one solution of the problem here, and we pull it back here, okay? And every time we go backwards, the volume increases here, okay? So if we pull back the solution of the Yamabe problem to this space, when we compute the energy here, this will be increased. And here it will be increased again. And at some point it becomes so large that it becomes larger than the energy of the solution of a sphere. And remember that the sphere has the minimum possible as the maximum possible minimal energy. So if I get a solution with higher energy, it means that it cannot be a minimum of the Yamabe functional. So at some point when I pull back, I have to have another solution which is the minimum, okay? The pullback of minima cannot be a minimum at some point, because it will exceed, its energy will exceed the minimum of the sphere. So by pulling back a finite number of times, we obtain another solution. But we can pull back infinitely many times because of this reason. So this is how the infinitely many solutions comes about. And I think this is a good time for stopping. Maybe I can show you a photo of my collaborators in this infinitely many solution problem. And I want to thank you for your attention, and I will stop here.
Thank you very much, Professor Piccione. Nice
Yes.
contribution. Questions? I know you. Yes, indeed.
I cannot hear you very well, actually.
All right, let's try to hear Henrique.
It's me, Paolo. Hello?
Hi, how are you? How are you, Enrique?
Doing well.
Should I go back?
You're good.
Oh, wait a second.
How about you tell people we have a full room? What are the current open questions regarding your Marvin type problem? What is the frontier of knowledge right now in your understanding? And where do you think conformal curvatures as an idea occurs?
I'm sorry, I cannot hear you very well, really. The audio is somewhat disturbed. Did you ask me about telling about open problems in this area?
Yes.
Yes, exactly that.
Yeah, okay. From an analysis point of view, these critical operators that arise are very difficult to study because, especially in higher order, because there is no maximum principle, and so there must be some a breakthrough in the theory of higher order critical PDEs has to be somehow invented to deal with this kind of operators. Results concerning the existence of solutions of problems that involve these operators are extremely sparse. So I think there are many challenges for analysts in this case. For geometers, really, we need to understand better the geometrical meanings of these quantities. What are the geometric properties that can be associated to Q curvature, for instance? Can we recover which global invariants we can obtain from conformally invariant from conformal curvature? Can we obtain the volume, for instance, of a conformal manifold, of a compact conformal manifold? Can we see how it grows at infinity in case of non-compact or things like that? So, how to use these conformal invariants and curvatures to obtain classical geometric invariants for manifolds? So I think these are open and difficult problems.
Thank you.
All right, guys. Any other contributions or questions to Professor Paolo? Well, not being that.
Yes, yes. Was it a question for me? I'm sorry.
Not yet. I'm trying to collect questions here.
Mm-hmm.
All right. I would like to invite you guys to thank Professor Paolo once more because it's 3 in the morning for him. It's not easy to be awake at this time in China. Thank you very much. Professor Paolo, thank you so much for making the time to be with us.
Thanks for having me, and sorry for the problems at the beginning.
Nothing to be sorry about. Thank you.
Yes. Okay. Thank you very much. Goodbye. See you soon.
Bye. Bye. Hey everyone. Thank you.